Good day, everyone. I am Carlos Baldo III from the Mapua University, and today I will be discussing magnetostatics. To begin our discussion on this field, we will consider getting the magnetic field produced by a moving charge. Here, our task is to get the magnetic field produced by a moving charge at point P. As you can see on your figure, there is a point charge Q that is moving to the right with velocity v, and we wanted to find the magnetic field it produces at point P, a distance r from the instantaneous location of the source charge. The formula to get the magnetic field is given by mu naught divided by 4 pi times q times the cross product of the velocity v and r hat divided by r squared. Here, mu naught is the permeability constant that is equal to 4 pi times 10 to the minus 7 Newton per ampere squared. Q is the charge. V is the velocity of the moving charge. R is the magnitude of the distance of the charge from point P. And R hat is a unit position vector of the charge from point P. In terms of magnitude, we can obtain a magnetic field following this formula. Mu naught divided by 4 pi, absolute value of the charge Q times V, sine phi divided by r squared. Here, the angle phi is the angle between the velocity and the unit position vector r hat. Angle phi is measured from the velocity or the speed v up to the position of the observation point P. As a remark, here we can notice that the magnetic field magnitude, just like electric field, is proportional to the charge and to 1 over r squared. Recall that electric field produced by a charge is given by the absolute value of Q divided by 4 pi epsilon naught r squared. Based on this equation of the magnitude of the magnetic field, we find that the magnetic field is maximum if r hat is perpendicular to the velocity. That is, if point P is located perpendicular to the velocity or speed. On the other hand, the magnetic field is zero if r hat is parallel or anti-parallel to the velocity. That is, if the position of the point or the point itself is along the charge trajectory. Remarks. We take the absolute value of the charge, that is, we ignore the sign if we are to get the magnitude. B is maximum when measuring it perpendicular to the velocity or speed. B is zero when measuring it along the charge's trajectory. The source charge cannot feel its own magnetic field. We are measuring B or magnetic field at some other location but not on the source charge itself. Now, in terms of direction, we are to use right-hand rule. In this way, we are to orient our hand following the figure here. As you can see, the pointing finger, the thumb, and the middle finger are all doing an L shape with respect to each other. In doing the right hand rule to obtain the direction of the magnetic field, we have to orient the pointing finger along the first quantity, in this case is the velocity of the source charge. Then We have to move our middle finger along the second quantity, which is r hat, or the location of the point wherein we're measuring the field with respect to the velocity v. The thumb will automatically give us the direction of the magnetic field. To apply right hand rule, we are to use it here on this given figure. Here the source charge is positive. The red arrow indicates the direction of the velocity, and the green arrow corresponds to the position of point P, or the direction r hat. We have to use our hand to do the right hand rule, or yet our pointing finger along the first quantity, which is the velocity. Then we have to orient our middle finger along the second quantity, which is r hat, or the position of the point. Where is your thumb pointing? We can verify that our thumb is pointing towards us. That is, the magnetic field is also pointing towards us. The direction towards us is also out of the page, or with respect to the page of the screen. If the charge happens to be negative, then we are to do the right hand rule first, assuming that the charge is positive. Eventually, we have to reverse the direction that we have obtained since the charge is negative. Thus, for this example, we can verify using right hand rule that the magnetic field at point P is pointing away from us. With respect to the page of the screen, that direction is into the page. Notice that magnetic field is both perpendicular to the velocity or speed and to point P. Magnetic field or magnetic field lines form a closed loop. To verify that, we can consider four different observation points labeled W, X, Y, and Z, and obtain the magnetic field produced by this moving charge moving into the page on these four observation points. At point W, by doing right hand rule, we can verify that the magnetic field is to the right. At point Y, the magnetic field upon doing right hand rule is downward. At point Z, the magnetic field is to the left. Lastly, at point X, the magnetic field is upward. Hence, we find that these tangential directions of the magnetic fields at points W, X, Y, and Z are actually forming a circular path. Hence, that correspond to the magnetic field lines that indeed is forming a closed loop. For a moving charge, it produces both magnetic field and electric fields. For example, for a positive charge that is moving into the page, it produces an electric field that is radially outward. At the same time, there is a magnetic field that is directed clockwise. Notice that the electric field and the magnetic field are both mutually perpendicular to each other. To test our understanding, we are to answer problem 3.1. In this problem, we have a positively charged particle moving towards the x-axis or the negative x-axis as shown in the figure. There are two observation field points, namely Q and R, that are both equidistant from the charge and are both along the xy plane. Which of the following is correct about the magnetic field at these two observation points? We have five possible choices. Now, to answer this question, first we compare the direction of the fields doing right hand rule. For point Q, the velocity of the charge is to the left. Point Q is located above this instantaneous position of the charge. By doing right hand rule, we can verify that the magnetic field is into the page. At point R, still the charge is moving to the left. Point R is located somewhat northeast direction. Doing right hand rule, we can verify that the magnetic field, as denoted by our thumb, is pointing into the page. Here we find that both magnetic fields at point Q and point R are both into the page. Then we compare the magnitude of the fields produced on both points. For point Q, the magnetic field is equal to mu naught divided by 4 pi times QV sine 90 degrees divided by r squared, since point Q is located exactly perpendicular to the velocity, which is to the left. On the other hand, for point R, the magnitude of the magnetic field is given by mu naught divided by 4 pi QV sine phi divided by r squared. Here, angle phi is less than 90 degrees. So clearly, we find here that in terms of magnitude, the magnetic field at point Q is greater than the magnetic field at point R. Earlier, we have discussed how to get magnetic field produced by a moving charge. Now, at this point, we are to discuss the magnetic force acting on a moving charge. Our task is to get the magnetic force acting on a test charge Q. It is given by Q times the cross product of the velocity of the charge V with the magnetic field capital B that it experiences. Take note that the test charge feels the magnetic field, and this magnetic field is not produced by the charge. In terms of magnitude, the magnetic force can be obtained using this formula. Charge magnitude Q times the velocity V times the magnetic field capital B times sine alpha. Here, angle alpha is the angle between the velocity of the charge V and the magnetic field B. It is measured from the velocity or speed V up to the external magnetic field. If we are to compare this magnetic force to electric force, then we find that both magnetic and electric force are proportional to the corresponding fields. Electric force is proportional to the electric field as magnetic force is proportional to magnetic field. From the formula of the magnitude, we find that the magnetic force is maximum if the test charge is moving perpendicular to the magnetic field. The magnetic force is zero if the charge is moving parallel or anti-parallel to the magnetic field. Remarks. Again, we take the absolute value of the charge, that is, we ignore the sign. Only the velocity component parallel to the field will give us a zero magnetic force. Zero magnetic force if the charge moves along the field. Now, in terms of direction, again, we do right hand rule, but notice that we have some modifications. Here, the velocity v is the velocity of the test charge. We are still to orient our pointing finger along the velocity. The middle finger this time is oriented along the direction of the magnetic field. Automatically, our thumb will determine the direction of the magnetic force. Let us apply what we have learned in getting the direction of the magnetic force to this given example. Here we are to consider a positive charge that is moving into the page. The magnetic field it experiences is upward. By doing right hand rule, we can verify that our thumb is pointing to the right. Therefore, the magnetic force is to the right. If the charge happens to be negative, then we are to do the usual right hand rule, assuming that the charge is positive. Eventually, we are to reverse the direction that we have obtained. Now, if we are to compare the motion of two charges having the same magnitude but different in sign, then clearly we will find that they will move to different directions when they are both exposed to a uniform electric magnetic field that is into the page. The magnetic force causes deflection on the moving charges. Now at this point, we are now to identify the difference between the source and the test charge. The source charge is the one that produces the field, whereas the test charge is the one that feels the magnetic field produced by the source charge. Here we have a source charge positive QA. It produces a magnetic field at point P given by the magnitude mu naught divided by 4 pi times QA VA sine 90 divided by RP squared. RP, as can be seen on the illustration, it is the distance of point P from the instantaneous position of the source charge positive QA. VA is the velocity of QA. By doing right-hand rule, we can verify that the magnetic field produced by QA at point P is directed into the page. Now, if we are to put another charge, negative QB at point P, then it becomes a test charge. Being a test charge, it will feel the magnetic field produced by positive QA. The magnitude of the force experienced by negative QB due to the magnetic field of positive QA is given by QB times VB times BA sine 90. By doing right hand rule, we can verify that the magnetic force acting on negative QB is to the right. On the other hand, negative QB can also become a source charge. It produces a magnetic field on the location of positive QA. The magnitude of the magnetic field produced by negative QB on the location of charge QA is given by mu naught divided by 4 pi times QB VB sine 90 divided by RB squared. Now, in terms of direction, the magnetic field produced by negative QB on the location of positive QA is into the page. Now, if we want to find the magnetic force that positive QA experiences due to the magnetic field produced by negative QB, then it is given by F on charge QA is equal to QA times BA times BB sine 90. Now we are ready to get the magnitude of the force that positive QA experiences due to the field of negative QB. The magnitude is given by QA times BA times BB sine 90. By doing right-hand rule, we can verify that the magnetic force acting on positive QA is directed to the left. Notice that magnetic forces acting on these two charges actually exhibit action and reaction. Here we have basically two oppositely charged particles that are both exposed to the same magnetic field that is uniform. The result will give us the same amount of force, but they're different in terms of direction.